So we've got this chart of body weight versus brain weight. And it looks kind of linear, huh? What is making it look so linear? The elephant. Yes. The human, the dolphin, the hippo, the elephant don't really fit at all. So what do we call that elephant? No, special name for it. Special name for this type of outlier. Influential observation. The outliers in the x direction are called influential observations because they pull the line towards them. The human and the dolphin would be considered outliers because there's plenty of things in that body weight range. So outliers in the y are outliers. The hippo might also be an influential observation, which is why the thing doesn't go almost through the elephant. So if we take out those four, we get a graph that looks like this, which looks a lot more logarithmic than linear, doesn't it? So we're going to do a transformation. And what they did was they took the logarithm of all the values on the x-axis and all the values on the y-axis. And now it looks pretty linear. So this is probably actually a square root graph. So a couple important things. Monatomic functions means it's only moving in one direction. As t increases, or as whatever in the x-axis increases. ANI2, please keep it down. So as I'm going left to right, it's either going up or down. So monotonic increasing would mean it's increasing the whole time. Monotonic decreasing is decreasing the whole time. Okay. A graph that looks like that would be non-monotonic. Okay. So what happens when you transform a monotonic increasing? When you log the axis, it keeps the order the same. When you do a monotonic decreasing, when you log it, it actually reverses the order of the data. And so here's some basic graph shapes. Linear, y equals mx, y equals negative mx. Are the lights flashing? Okay. So these are kind of what these look like roughly. You know pretty much all of those. Maybe the 1 over square root of x, you're like, oh, that's a little different. But 1 over anything x kind of looks like that reciprocal function. The transformation ladder kind of looks like this. The thing about this p negative 1, like this p to the half is like square root. This p negative 1, it's because it's switching the order that it doesn't quite look like the reciprocal. I wouldn't focus too much on that. Don't get hung up on that because we won't do much with this. Okay. Okay. A country's gross domestic product and life expectancy. Okay. Here is the life expectancy versus gross domestic product. We got three here that really don't fit, but otherwise we have a pretty curved pattern, don't we? So what we're going to try to do is make this linear because all of our things on linear regression work pretty well. Um, you guys didn't execute this very well, but on the test, is the slope is equal to, I believe it's this. Oh. Let me grab the book. There was one on the test where they gave this to you. And yes, calculating that by hand would still be a pain in the butt, but it's absolutely doable. Some of the other ones, I think this is what the calculator actually does. Yeah. Those are very important. So if we can get our data to be linear, we can calculate this. And we could do this before we had technology to do it for us. But I think this is also how they're programming it, is they're linearizing it and taking it out, is how they program the calculators. So, it's important that somebody still knows how to do it by hand. Otherwise, you can't program it. So the square root of GDP is basically taking everything on the x-axis and square rooting it. This does the log. This one's probably the best. You can see the R values here. I think this is probably the most realistic. This one divided by the square root. You do get a slightly better R value, but I'm not sure that this is a sensible transformation. So at some point, sometimes you don't just base it on the R value, you base it on what does reality seem to indicate. Okay. And there's one that we're going to do that's going to be a cubic, and it makes way more sense for it to be a cubic than it does to be a anything else because the relationship between its length and weight is like your volume related to your volume, which is 3 dimensions based on length is one. So it makes more sense for it to be that than exponential, even if exponential would fit it better. Because there's a physical relationship between length and weight usually is a 3 dimensions on the length. If you don't have any way to tell or predict, you'd probably want to use just try several. So let's look at how to do this. This is exponential growth. You can see that very clearly. So the growth of money, dollar invested at 6% turns into $1.06 in a year. The original remains, you earn 6% interest. So if the Native Americans who sold Manhattan Island to the settlers for $24 in 1626 had deposited their $24 into savings account with 6% annual interest. You cannot currently get that in any savings account. I don't think it's ever been that high in my life, but the stock market usually is that high. So their money would be worth 80 billion. Now, $24 was a significant amount back then, worth probably millions of dollars now. But at the same point, oh, it's only worth millions instead of 80 billion. And that number would be more today. This was based on stuff. By 1826, 200 years later, though, it only would have been 2.7 million. Exponential growth starts to grow really, really quickly after it takes off. It doesn't grow very quickly at first. So, cell phone use. I want you guys to take this data, take your book, flip to page 205, enter this data into your calculator. I'm going to show you how to do this. So once I've got it all entered, I'm going to make a data and statistics graph of year versus subscribers. It looks kind of exponential. So now I'm going to do, and I'm going to make another column called log sub. And in this formula bar, I do not need to enter the equals, it will by default. I'm going to enter a formula, log base 10 of my sub column, or my subscribers column. And I hit enter, and it takes the logarithm of everything in that column. That makes sense. So in this column, I have log base 10 of sub. You can see it down at the bottom of the screen, the formula. So it's a little simple programming. You guys got that? So instead of doing them all by hand, I'm just letting the calculator do it for me. And now I'm going to go back here and I'm going to grab graph year versus log sub. That looks significantly more linear, correct? But what you're going to notice with this one is I've got a trend line that fits these four really well, and one that fits these four really well. Actually, kind of, nope, I tried to go through five. These four. So if I want to predict how many cell phone subscribers I'm going to have in the year 2000, I should probably just use my last four because it appears like the line changed, didn't it? So before I make my regression, I'm going to go back and delete my first four data points. I accidentally deleted my formula. So now I've just got this, and I can do menu, analyze, regressions, show linear. And I get this. I can also do it from the calculator page. Menu, statistics, stat calculations. Year. Do you guys, if I showed you this, the F1 thing, pay attention to what that one, just use whatever it defaults to. But if I want to plug in a value, I can just use function notation.
Oh, right.
I was like, I think I showed that a while ago. Now, the unfortunate part is that still returns the logarithm of that. So we're going to talk about how to take my logarithm and turn it back. Because what I really had here was log y equals 0.09699x. I am carrying a lot of decimals. Minus 188.951. And how do I solve this for y? I raise both sides to 10 to the power Okay. And the exponent rules say this. This multiplying the exponents is like raising it to a power, and subtracting is like doing, oh wait, no, is like times, because remember that I'm just doing these with tens. So knowing those exponent rules, I can get this, and I could get this into exponential form. This is going to be something tiny. But a normal exponential form would be, I don't know what 10 to the point zero. Here, let's just do it. And that's an exponential function. This a part in y in your standard y equals ab to the x is really, really tiny. But b is now kind of a normal number. Does that kind of make sense? If I wanted to predict for the year 2000, I could really take any of these versions. I would probably just do this and stick it into my calculator. I probably wouldn't use this one, but the less I round, the better, especially with exponentials. You better have at least three places past the decimal with exponentials, but like I've got five on the one. Well, you better have at least three places past the decimal that are significant. Okay. Does that kind of make sense? You you get your line, you undo it. So now we're going to do one that's versus a power law. And the first thing I'm going to do is give you an example of one and show you how to undo it, and then we'll do the whole thing via the calculator. So for a power law, remember, how do we, oh, quick before we go, how do we check if something should be linear? Linear regression is good. We have what in the residual plot? No pattern. So this was our one that we just did with the cell phones. Originally, we had to have a distinctive pattern, right? That's why we do. That also was a clue that we should delete the first four. There is an absolutely distinctive pattern. Even though when you do delete the first four, you still have a pattern, but these residuals are tiny. The residuals will generally be small when you take logarithms, but these ones in particular are really small, 0.0015 versus 0.8 or 0.08. So a lot smaller. So basically what we're going to be doing here is exponentials and power functions. Exponentials y equals ab to the x. Power functions y equals a x to the b. Remember power functions from last year? They are all single term. It's x to a power. That power does not have to be a whole number, though. And you have a coefficient. So we do this brain weight one. We are not going to enter all the data. Remember that the predicted y is y hat. And that just means predicted. And this is my essentially mx plus b. So with exponentials, you log y-axis. If you see an exponential looking graph, log y. If you think it's power, log x and log y. So that means my actual equation is this. They reverse the order. It's the same thing either way. So I do 10 to the power of both sides. Giving me y hat that plus 1.01 is still in the exponent. So I used one exponent rule where I separate those two. And then I used my laws of logarithms to bring this to the exponent. Does that make sense? So the multiplier in front of the log goes to the exponent. Now, those are inverses. 10 to the log 10. Giving me, I'm going to move this to the front. And 10 to the 1.01 is 10.2. So whenever you can get a reasonable number out of that, get a reasonable number. That looks like a normal power function, doesn't it? So there's some algebra here.
Good.
It's not horrible algebra, and it's kind of the same every time. But you got to know you have to be able to use the two rules of exponents, the multiplying one and the adding one. If it's subtracting, I always just do it as a negative exponent. I just add the negative. And then you've got to know these laws of logarithms, the inverse thing, and really just the one where you bring it to the exponent. So let's do a whole problem with this. And I think fishing tournament. And yes, I've used this. You did this on a pre-calc test.
Oh,
You did not have to do it this way. You have to show me you're doing it this way when you do it on the tests. But so we have fish length versus weight. And this is length being one dimension, weight being three. Tells me I probably don't want this to be exponential. I want it to be power law. And I do not need to, the age column is completely extraneous information. So I'm going to do a regression, length versus weight. And what they're essentially doing is it's very hard to weigh a fish because when they're flopping around, you don't get a consistent weight. So for the tournament, they measure length and then they estimate it to weight, which, and you're based on your weight. But I'm like, what? I don't get that. I'm like, just measure it on the length. Why, if you're just going to convert length to weight anyways, but maybe there's more prizes for the weight that weight grows in three dimensions. So notice this weight is going up a lot more than this length.
yeah.
So here we've got 20 different ages of fish. This data is on page 216. So go ahead and enter all of that data into the calculator. And then I logged both axes. hmm So I made a log length column and a log weight column. And you can see kind of the formulas down here at the bottom. Then when we've got these, we add our data and statistics graph. And if we look at length versus weight, it looks exponential, but that could also be cubic looking or possibly quadratic. Since we have the idea that it's probably cubic, we're going to do log on both axes. And that makes it very linear. And if we do menu analyze, regressions, show linear, we get it showing up pretty nicely. If we look at our residual plot, do we see any pattern?
No.
There's no noticeable pattern there at all, is there? Which means linear was a good fit for this one, meaning ultimately my equation of log of W hat for weight equals L for length. You can't read that very well. Is a very good equation. How do I transform this? How do I get rid of the logs?
Oh, right.
10 to the power of everything, giving me predicted weight was 10 to the 3.049 log L plus negative 1.899. Ten to the log L to the power of 3.049 times 10 to the negative 1.899. Can one of you guys do 10 to the negative 1.899? Negative 1.899. 0.0126. 0.01 what? 18. Okay. Then these are going to cancel. So L to the 3.049 or W equals 0.0126 L to the 3.049 is my power law equation. Does that kind of make sense? It's like you have to practice these. You gotta just get the calculator thing down, but that's all there is to this. How did I get the residual? So I went menu, analyze residuals, and then show residual plot. So analyze, it's number 7 is residuals. Show residual plot. Mine it says hide now because I'm currently showing it.
Grayed out.
Yours is grayed out. Have you made the regression line yet? You have to make the regression line before it will show the residuals. That's a good question.